Thank you for being here. My name is Antonio Fernández Anta, and I work at India Networks Institute in Madrid. Well, I collaborate with Sebastián and Maria in computer science, but what I'm presenting today is a little bit outside my main area of work or my main area of expertise. This is something that is a project and we started in March due to the the coronavirus pandemic. As you see, there's a huge list of co-authors. In fact, the team, if you go to the webpage of the project, we have already like more than 30 collaborators, and we have had more than 200 people involved helping with different aspects of the project. Essentially, why did we start this? Okay, this is the front page of El País, which is the biggest newspaper in Spain, and the fact that I want to show is that they were claiming that on March 13th there were just about 3,000 cases of COVID-19 in Spain. Okay, that day it was obvious that this number was wrong. Essentially, we knew, and it was all over the news, that the number of tests that they could run every day was very, very limited, that it was impossible to confirm every case, every person with symptoms, and there was no way or no simple way to know how many cases there were actually there, you know. So what I did is I ran like a toy experiment. I went to Twitter and I asked the question that probably you should be able to translate very quickly. What I asked is, how many people do you know who had symptoms of COVID-19? I got 700 responses. As you see, you know, most of the people didn't know anybody. But then you have a few people with one person in their environment who had symptoms, 2 persons, and then 7.8, 3 or more. Just assuming that 3 or more means 3, and assuming that every participant knows 150 people, which is this well-known number in sociology called the Dunbar number, which is like, you know, essentially it's is how many people you can maintain close contact with at any given point in time. I got a rough estimate of 150,000 infected by March 14th, you know, which is when this Twitter survey was run for 1 full day. That means that if this number, and 150 people is a lot, so that means probably this number was already undercounting. That means that the official numbers were 50-fold smaller than the ones that I was estimating. So from this main idea, it evolved into what if we do that at a much larger scale. So I started talking to other people in other countries, and we deployed similar surveys in Twitter initially, in Portugal, Italy, Cyprus, UK, US, and just a little bit of time later, we moved to Google Forms, because it was you know, Twitter was not flexible enough. It was only giving us four different potential answers, and eventually we made it into an academic project. So I got all the ethical approvals from my institution. And one of the things that they decided in my institution is that they would only give me the approval if we move out of Google Forms to our own server. So right now what we have is a survey that kind of asks the same question that you saw before in Twitter, and is surveying people who are reporting indirectly the health status with respect to COVID-19 of their contacts. So the survey now is available in all the countries in the world. In 150 of them, it can be filled at the regional level. Actually, in France, it can be filled at the department level, and it is translated to more than 60 languages. So just to give you an example of roughly what we ask for is, well, you choose a country or a region in the country, and we ask a question, which is, how many people do you know personally in this area, in this geographical area? This is essentially to get what would be similar to this 150 Dunbar number. So instead of trusting that Dunbar was right when he was proposing that number, we say, okay, you know better, you participant who is giving me your information, you know better. How many people do you know? And then I want to know how many of those that you know had symptoms or was diagnosed with COVID-19. This is roughly all we ask for. At least this is all we ask for in the very early version of the survey. And what we have here is the answer to the first question is what we call the reach, is how many people do you reach with the answer to this question. And the answer to the second question is what we call cases, which is essentially how many cases this question is reporting. Then applying a technique that is called the network scale-up method, we can estimate the proportion of the population that has been infected or has had symptoms by just simply summing the cases and dividing by the sum of the reach. This network scale-up method is something that I didn't know when I came up with this Twitter survey. It's something that we have discovered later on that it exists. Surprisingly, it's a very recent statistical tool. It was implemented for the first time, or it was used for the first time in 1985. And as far as I know, this is the very first paper in 91, reporting, applying it in several contexts. It was used for the first time in 85 in the Mexico City earthquake, in which they had problems accounting the number of fatalities. Of course, you could not ask people, are you dead? So what they did is they asked people, how many people you know, and how many of those that you know are disappeared or are missing or died. And using that, they were able to estimate the number of fatalities until a proper accounting was available. Essentially, our target is doing the same. We from 3,000 to 150,000. We don't aim to have an exact number of how many cases of COVID-19 were in a given region, but we want to be off from the real number by maybe no more than one order of magnitude. We want to kind of close a little bit the gap between the official data and the real data. Just to give an intuition of why or how this works, let's say we have this social network and we want to estimate the ratio of people in this network that have either glasses or a beard. Okay, I just did some quick counting, and I found that there are 102 persons in this network, out of which 24, the ones with the blue circles, have beards or glasses. So that's 23.5%. Now I want to estimate this number by sampling, and I'm going to be doing two forms of sampling. I'm going to be doing direct sampling. So in the direct reporting, I'm going to ask one person, do you wear glasses or do you have a beard? In the indirect reporting, I'm going to ask a person, the same person actually, among you and your contacts, how many are they and how many of them have beards or glasses? So if I do it once, on the left, I'm sampling one person. If I apply an estimate of how many people reported having glasses or beards with respect to how many people I asked, I get an estimate of 0%. On the right, you see that, you know, with just sampling one person, just asking one person, I got information of 7 people and giving me an estimate of 28.6. The ground truth is on the down right is 23.5. So I'm already not far from reality. I mean, from the actual value. Then I sample a second person, and again, you know, in direct reporting, I get an estimate of 50%. Indirect reporting is giving me 21.4. Okay, let me do it once more. The direct reporting is getting a little better. 66 actually is getting worse, but well, eventually will converge. 66.6.7. While in my case, I'm estimating 25%. Observe that I am counting twice some people because I'm asking someone who has common friends, common acquaintances with the very first person I asked. But that should not change the result. In fact, what we have done, and these are results from this week, we've been doing some simulations trying to compare these values in real networks. On the left, what you see is the result we get in the DVLP in a DVLP subgraph, and on the right, what you get is what we show is the results in a subgraph of Facebook. One has 300,000 nodes, the other one has 4,000 nodes, and as you see in both cases, the error, you know, the top plot, decreases much quicker using the network scale-up method. And at the bottom, you know, in this particular case, the number of nodes or persons that were infected was 1%. So as you see with the network scale-up method, very quickly the red line gets very close to 1%. Especially the Facebook case is probably like with 20 people asked, we already have something very, very close to the 10% that we were looking for, while the blue line takes much longer to converge. In fact, in Facebook, it doesn't really converge even after 300 rounds. In this particular experiment, we are assuming that the distribution of infected cases is uniform, you know, uniformly random, and we also assume that the sampling is also uniform. But this shows that this network scale-up method is, we believe, quite powerful. Now, going back to our CoronaSurveys data, we collected especially. I mean, we've been collecting a lot of data or a lot of responses, mostly from a few countries, Spain, Portugal, Italy, France, surprisingly, Ukraine, UK, Greece, Cyprus, US mostly, Germany also. Some other countries were fighting, and Brazil and Ecuador. But by far, the country in which we got more responses is Spain. And we were lucky that in end of April, early May, there was a serology study done in Spain in which they tested 60,000 people all over the country for antibodies of COVID-19. In particular, the data we are using is for an antibody type called IgG. So what I'm showing here in this plot is how the estimates of percentage of people that had the COVID-19 in the different regions of Spain compare with the results that this study called NCOVID-19 show. So the closer we are to the main diagonal, the better. So the dots that we estimate, or the values that we estimate, are shown in red dots with the name of the region on top. We have also applied another technique, which essentially uses the well-known parameter in epidemiology, which is the case fatality ratio. This is essentially the percentage of people that having symptoms end up dying. So this case fatality ratio, the case fatality ratio we're using is the one measured in the earlier stages in Wuhan, which is 1.38%. We know that this case fatality ratio is evolving, and in fact, probably the actual case fatality ratio now, at least in developing countries, is a little bit lower. But in any case, this is the one we use for this study, and what we do is we apply a correction, because we don't want to count cases that died today as cases today. We have to count them on the day they were infected, which is typically between 2 and 4 weeks before. So by applying this correction, we obtain an estimate that we call the CCFR, which is corrected case fatality ratio based estimate, and is the one shown in blue. So as we observed, both the blue dots and the red dots are not very far from the diagonal, which for us was very surprising. I'll tell you exactly now why. Not only that, when we look at the whole country, essentially what we do is we ask, most of the answers we get are the province or regional level, and then we aggregate them to get an estimate for the country. And what we found out is that the difference between the overall incidence estimated from the serology study in the whole country, which after correcting by the errors in the testing and so on, was like 6.3, I believe. Our estimates, both with CoronaSurveys and with the CCFR-based estimates, were off by I think ours was like 6.4 and 6.5 or something like that. So they were only off by one. We're talking percent. So less like 1/10 of a percentage point, which was honestly was very surprising, especially because the CoronaSurveys was obtained from 3,000 responses, actually less than that, while the serology study involved 60,000 people. In fact, they are running 3 waves, but I'm just reporting the first wave, which implied deploying medical teams and running 2 tests in every person over 2 weeks, which probably in terms of cost was no less than millions of euros. We're probably talking 1-2 million minimum. You know, for us, the 3,000 responses was collected with our survey, which, well, unfortunately, we don't have any funding yet. So all the collection and all the deployment that we have done so far has been by using volunteers and using a little bit of funds from leftovers from some of the projects. So we have developed different techniques to try to estimate the different pandemic parameters from the responses we get. We are not 100% happy with any of them, but all the data is available. So if you want to create your own estimate algorithm, you're free to do it. All the code that we use also is available. Everything is in GitHub. But let me just very quickly show the 2 estimates that we found that have the better performances. CCFR, which is the one that I was telling you about, and doesn't use the survey data. It only uses the confirmed fatalities and the confirmed cases, and the CFR used in Wuhan or measured in Wuhan. And we found out that the 300 responses estimate, which essentially for a given country, it takes the 300 latest responses and just applies this N-sum technique to those responses, is typically giving a reasonably good estimate as well. Here you see that the difference in Spain is only 0.7%, which is not a lot. And we found out that in most countries, these 2 estimates are in fact well in line. We started, the 30 responses that we have there is one that we tried at the very beginning, and as you see, it's a little bit off. So we are in the process of dropping that. And of course, what you see is this big gap between the confirmed cases line, which is the green line, and all the other estimates. So, and this is logarithmic. So we're talking a huge distance between, in fact, it's almost an order of magnitude difference. As I said, we also have data from Brazil. And I was surprised to find out that actually our estimates from the 300 responses and from the 30 responses and the CCFR in mid-May, they were very, very accurate. As you see, they've been diverging, which is not surprising because in Brazil, what we've now the difference between the 300 responses estimate and the CCFR, well, this is only, I'm only showing data until July. We have the data until yesterday in the webpage. I'll show you the webpage in a minute. But you see that now the difference between the 300 responses and the CCFR estimates are bigger. And so it's almost 1 point in percentage. And we believe that this may be due to the bad quality of the data. In particular, this is a symptom that we have found in other countries, like Ukraine, for instance, in which the CCFR estimate and the estimates we get from the surveys vary a lot. They have a huge gap. And this is typically because the number of fatalities reported is not accurate in those countries. We observe a similar phenomenon in Ecuador. Again, you see that the difference between 300 and CCFR is much bigger in Ecuador. Again, this is probably because there are many unreported fatalities, or at least they are not assigned to COVID-19. Maybe they are assigned to other causes. Just to conclude, let me tell you that, well, I'm just presenting here one application of this network scale-up method that we have used to estimate the evolution of the pandemic, and we believe that this is going to be very useful, especially in low and medium income countries and countries in which the data is not reliable. We have found that that is the case in some countries like in Eastern Europe, Latin America, and Africa. We have found is that the estimates we get are reasonably okay, even with a very limited number of responses. Between us, the total number of responses we have gotten from in our survey is 17,000. 17,000 is nothing compared with the number of responses that other surveys are getting. And however, we are able to get estimates that are reasonably okay. From these numbers, probably you can guess what is our main challenge, which is how to maintain a constant flow of responses. People get tired. Every now and then we send some messages over social networks asking people, why don't you fill the survey? But they do it, then they don't do it for a month, and they do it again. Well, this is what we have, right? We've been working on how to expand this to, for instance, detecting and forecasting bursts, and I'm going to show you a little bit of that in the web page. If we have time, let me go to the web page. You're still seeing my screen, I guess, right?
Yes.
Okay, so this is our web page. So this is essentially, you can come here and select France and, fill the survey. Here you can choose a region or a department if you want. And essentially, these are the main questions that I was showing you, like how many people you know and how many people of them has been sick or had symptoms. And as you see, we added some other questions like, you know, how many of them are still sick, how many started being sick 7 days ago at the oldest, and how many died. We added these questions because this is something that could help us to tune the parameters of the models. And this is because we want to estimate whether there are bursts. So for instance, here, this is one of the pages in which we're showing estimates. And for we have deployed this survey in one region in Madrid. Actually, these are 2 towns near Madrid, Rivas and Arganda. And for these towns, here we're tracking every day how many cases we estimate that every district of those towns has had in the latest 14 days. So this is in percentage. I don't know, in Spain, they typically report this data as number of cases per 10,000 people in the population. But as you see, you know, all these 4 districts are showing a pretty big ratio. I mean, we're talking Arganda is right now is declaring, I mean, these estimates that I'm showing are typically computed from like 10 to 20 responses every day. So it's not a lot, but it gives a pretty reasonable idea of what is happening. If you want to multiply that so this is per 100. So if we multiply by 1,000, we get the number that they are typically using, which is 4,000, almost 3,000, 1,500, and 1,000. Right now in Spain, they passed an order last week in which a city with more than 100,000 people and whose rate is 500 cases, confirmed cases, has to be confined. That means all these 4 districts exceed that rate, in some cases by almost 10 times. So we are, in Madrid, we're in a pretty bad situation. These are estimates that we obtain, you know, like number of fatalities and so on. Then, these are global estimates of infectious cases. We don't use the surveys for this map. Sorry. For this map, what we're using is the confirmed number of fatalities and the confirmed number of cases. We apply the CCFR estimate, and then we transform that into a daily number of new cases, and then we propagate that over as many days as we estimate that a case is infection, which in this particular case we use 12. We assume that from some article we got the magic number of 12, meaning that since a person becomes symptomatic, he can propagate the virus for 12 more days. So as you see, France, we're talking 1.15%, which is pretty high. Spain claims to be 0.9, but it's because the data is not reliable. Andorra is actually pretty bad. And if you are interested, you can see what is happening in France. This is just the same. What we're showing here, the green section of the bar is the number of confirmed cases. The yellow section is the cases that we estimate are there but have not been identified, have not been detected. Then we have estimates at the country level of these are cumulative. You know, how many people have passed the COVID-19 or have it right now. Then, for instance, you can look at France. Yeah, for France, we still have the 300 responses estimate deployed, but as you see, well, Our estimate is that CCFR is quite reliable, and that our estimate is that 4.5% of the population of France has already passed the COVID-19. That's our estimate, which we could find. Yeah, which is something like 3 million people. These are the official numbers, 600,000. This is the number that we estimate, like 3 million. And just let me say that everything is available in GitHub. So if you want to take a look at what we have there, we have code, data, estimates, everything. And that's about it. I don't think I have much more to say now.
Thank you, Antonio. Thank you very much. So, any questions?
Hello, thank you very much for your talk. How easy is it to mess with your system by a motivated attacker? So how can you prevent people causing lockdown in random places just by manipulating, let's say, many responses to the surveys or kind of skewed numbers, etc., etc.?
Okay, this is connected to something that I didn't mention and I didn't emphasize. The data that we collect through the survey is completely anonymous. Essentially, we don't collect any personal data. That is the reason why we put all the responses we collect, we put them available in GitHub as we collect them. I mean, with a minimum processing. We don't really touch them. So that means essentially that we cannot prevent any form of attack. Like if people want to, in fact, we found that people it is not unusual that people just answer whatever they feel like. We have found like very strange responses, like I don't know, somebody who knows 1 million people and all of them die, things like that. What we do is we apply a outlier detection. Before applying the estimates algorithm, we do apply outlier detection. So we detect how many people, for instance, people that report too many friends, too many contacts, people that report too many deaths, people who report too many cases. In some cases, it's not because they want to attack the system, but in some cases, it's because they could be like doctors in a hospital. And a doctor in a hospital, probably somebody that knows a lot of cases, and you don't want that particular piece of data to influence your estimates. But honestly, we don't have a full control of what is happening, in part because the ethical committee in my institute said that you should be careful with the privacy of the respondents. I mean, there is some things that we could try to do in order to avoid like a coordinated attack, and is only allowing people that we kind of trust to answer the question or go and fetch the people. In fact, we have tried to increase the number of responses by advertising in Facebook. So essentially, we selected in Facebook a certain region and say, okay, we want answers from people in this region. And Facebook was in charge of randomly selecting these people. Then the coordination was not possible. But well, anyway, I think I'm answering too much. Just to answer quickly, we don't, and we cannot prevent that. It's more something that has to be done in the post-processing or in the processing of the responses.
If I may ask a second question. So your work relies on two hypotheses. One, the cases are distributed randomly, and the second one, the sampling happens randomly. From the data, and this is kind of related to the previous answer, can you perhaps test whether these hypotheses are confirmed from your observations? So is the distribution of cases pretty random, and is the sampling kind of, let's say, also quite random?
Okay, I don't need to check. The distribution of cases is not random. I mean, it is clear that there is a lot of, especially geographic relevance. Like, let me give you an example. In the very first survey, we were not asking for regions; we were only asking for countries. So, as I said, we got a lot of answers from Madrid. Sorry, we got a lot of answers from Spain, but we didn't know where from Spain would these answers were coming. So we directly applied this network scale-up method, assuming that these answers were uniformly distributed around the country, and then all we had to do was, get the proportion, multiply the population of the country, and get the number of people that have been infected. What we realized later is that that was overcounting or overestimating the number of cases by a big number. Meaning the number at that point was probably around between 1.5 and 2 million of people infected, and our estimate was close to 3 million. What happened is that the promotion of the survey was more successful in Madrid, and Madrid had a much higher incidence rate than many other regions in Spain. Now the incidence rates can vary from one neighborhood to the next. So it may happen that you ask somebody to propagate the survey among their contacts. This person answers, and he knows many people just because he's in a neighborhood in which the incidence is high. He or she knows many people that are infected, but then all these person's contacts also know many people that are infected, and that could bias the results. So yeah, again, first, the virus doesn't spread uniformly at all. It has a very strong geographical bias. So that is something that unfortunately is a fact. Second, the sampling, our sampling actually could be biased as well geographically. We hope that the fact that we are asking for indirect reporting is going to spread the reporting more than direct reporting. Like, if you ask somebody, okay, tell me what is your health status, tell me, and pass it on to your friends, and then the friends report, then that may concentrate all the responses in a small area. Asking indirectly, I may report people that are completely outside my close circle of friends, but it could happen. So we have to think, and we have to identify means and techniques to avoid these potential biases. The geographical bias, we're already trying to fight it by not computing directly country level estimates, but the country level estimate is obtained by aggregating smaller level estimates, or smaller level answers. And that is giving a much better estimate at the country level. The fact that we are not sampling uniformly, unfortunately, it could be solved, but for that you need resources. Like if we have funds, which we don't, one thing that we would try to do is deploy massive Google and Facebook ads in such a way that they are the ones that make a random sample of the population. We are in touch with cities, and something that I'm proposing, like the small cities, like the ones I was showing, like Rivas and Arganda, And what I'm always proposing them to do in order to do this sampling uniform is that they can just go and check the census, select randomly in such a way that they guarantee that all demographic sectors of the populations are covered, and do the survey by telephone. You can just ask the same questions by just calling people up on their telephone. They don't need to have cell phones. They don't need to have web pages or certain computers or anything like that. And just by getting like 30, 40 answers from a city of 100,000 people, getting 30 or 40 answers every day on the telephone is going to give you a very good estimate of what is happening and which neighborhoods are in danger, in which neighborhoods things are okay. So that, at least our experience is that with very, very few answers, you get a lot of information.
I have a question, two questions, Jean-Luc speaking. First, did you observe some evolution in this estimation with the increased number of tests? Because now we have more and more tests, and so what is or not the correlation? How do you explain the low value in US compared to the reality? In fact, the figure in US looks very low compared to Europe, but they are in reality strongly affected.
Here you can see how, for instance, this is the US. We are taking into account that in our estimates. At least this is using the CCFR. In the surveys, the answers we don't use at all the official data. So the fact that they are reporting more cases or less cases is not affecting the answers. It is affecting in one aspect. At the very beginning, all the reports with the survey, all the reports we were getting were people that had symptoms, because the percentage of people that had been tested and confirmed without symptoms was minimal. What is changing is now we are getting more responses reporting cases that have been confirmed by a test without symptoms. So the number of asymptomatic cases being reported in the survey, we know that is increasing, and we haven't introduced any correction for that yet. Time is limited, so we are doing our best. The CCFR estimate of active cases that I'm showing here, as you see, the number, the green bar in this here is lower than the green bar here, and however, the total number of active cases is lower here than here. That is because we are taking into account the fact that this reporting is higher. That is the algorithm takes that into account. It applies the correction in the right way. It's essentially because the correction is not based on how many cases are reported. It's mostly based on how many deaths are reported, and deaths are a little bit more reliable than reported cases. Now, the question about the US, these are the official data, confirmed cases in the US, 7.5 million. Both our estimates are talking about 16.5 in one case, 12.9 in the other case. I trust more the 16.5 million people infected in the US. This could actually be also tested by applying, the Facebook in collaboration with CMU and University of Maryland. They have been running another test. They do only direct reporting, so they only ask for people if they have symptoms. And we are looking into how to use that data to get even a third way of estimating the actual number of cases. So that will give us CCFR based, the estimates obtained from our survey data, and the data obtained from the survey run by Facebook with these two universities. But well, we're still working on that. But yeah, I mean, I don't know exactly what you mean or what you meant by saying that the US data is low. They're underreporting the number of confirmed cases like everybody else. Like, you know, if you look at Spain, we're talking 100,000 official cases, while the numbers are close to 3 million. And this was already discovered. You know, when they did the serology study, they found out that no less than 5% of the population, which is 2.5 million, have been infected already. So they know that this 800,000 is completely unrealistic. But they just is the only thing that they have the authority, like real measure that somehow they use. It's like the Johns Hopkins data that you see. You know, you go to the Johns Hopkins plots, or most of the web pages where they talk about, you know, how many cases are happening in different countries, and what you see is these numbers, is this column, the number of confirmed cases. But this number of confirmed cases, as I said, is, well, is probably not very realistic. Sorry.
Fabien, you have a question?
Yes, I've got another question. So it's still related to a possible correlation and bias. But the question is, what if there is a correlation between the probability to be infected and the degree in the graph? And I will take a very extreme example to make my point. For instance, I guess that if right now you ask people in Washington, D.C. if they know at least one people in the neighborhood who's got the coronavirus, I think they will say at least one person. And of course, this is just for fun, but the more friends people have, the more likely she is maybe to get contaminated. And so can you take care of this bias in your project?
Yeah. I see that in the French version is not clearly stated, but maybe it has to do with the translation. But the question, the way it was designed and the way is being asked in let me see, English, is how many people do you know personally, or how many people do you know, like it's not like somebody you see on TV, like somebody that you know personally. And that is here. Like the question we typically ask is how many people do you know personally in this geographical area? Meaning you should not report about someone that you heard about. It's somebody that you know in person.
Okay.
That should, yeah. But you know, there's no, I mean, having said that, there's no perfect way, in our view, there is no perfect way of asking these questions without, you know, without having to like write a very long text, which would discourage people from answering. So we kind of, you know, anyway, sorry, but go on. Yeah, maybe I didn't get all the details.
Okay, so I remove the Trump example, but still my same question remains. What if you have a correlation between the number of people you personally know and the probability to be infected? Can you take care of this correlation?
Completely, it could happen. I mean, right now, as I said, I mean, okay, what you're saying, it may happen. Like somebody who's more popular may, in fact, be more likely to be infected because he or she interacts with more people. Yeah, that could happen. But there could be many other factors. There could be a factor of age. There could be a factor of the size of the city or the size of the population, the town where that person lives. So yeah, there are many aspects that we don't control. So as I said, I mean, having said that, I would love to be able to identify those cases, and I would love to be able to introduce corrections so our estimates are better by applying those corrections. As I mentioned at some point in the presentation, what I'm looking for, what we, our objective at this point, eventually we may want to improve this technique, but our objective right now is to get something that is not too far from reality. Like I must say that when I saw this result comparing, when I saw this result, and I saw that the estimate we were getting was almost on the spot. I was really surprised. I was expecting to see, I don't know, like twice, and that would have been a good result for me. Like, if I'm able to estimate how many people are infected within a factor of 2, I would have been happy. I'm still not sure that this is not a coincidence. It could just be that we were lucky. Well, if you look at the correlation of all the other regions, it looks like we were lucky multiple times. But still, as I said, all these biases that you are mentioning, we are aware that they are there and we have to live with them. All we can do is try to see if we can compensate one at a time. For instance, in order to try to compensate, we are to compensate for caused by somebody is recommending you to fill the survey and that person also filled the survey. We introduce questions like this last question, in which we kind of try to identify when there is a propagation of survey filling within a given community, and therefore the answers from those people may be correlated. Unfortunately, we cannot connect these two answers. If you say, yeah, somebody told me about this survey, I don't know who did it, so I cannot really tell if your two answers are somehow correlated because somebody who has been infected and it's a common acquaintance, But that is unfortunately that is what we are living with. Of course, something else to think about doing in the next phase of the project is to ask for more personal questions, like age group or gender or other aspects that could help us to tune a little bit the estimates a little bit more. But that would mean that we would be collecting personal data, and then we need to be careful, and we would not be able to share everything. So, but right now we don't have the resources to apply that change to do that.
Hey, ask a last question for me. What's your Dunbar number? Is it the same? Is it radically different from your empirical evidence?
Okay, yeah. My Dunbar number is probably not too far from 150. However, this is something that is a cause of noise, and so something that I kind of cheated when I was trying to sell you that indirect reporting is wonderful. Indirect reporting is wonderful if you know how many contacts you have exactly, and if you know how many of them are infected exactly. And of course, neither of the two parameters are easily obtained with reliability. Like for instance, typically for Madrid, I say that I know 100 people. I think I do know many more people than that in Madrid. And there are people that had COVID. I only found out like maybe 1 or 2 months after. So my report of how many people I know and my report of how many people had symptoms among those I know, in both cases, is not accurate. I go back to my previous statement. Hopefully they are close enough. But yeah, Dunbar number for personal relationship is not too far. Let me say that once we remove outliers, the average number of contacts that people are reporting is 60. So I would say probably 6. To me, 60 is in the low end, but because we are asking how many people do you know for which you know their health, probably makes sense. That is way lower than the Dunbar number. So probably 150. In fact, we tried to do some estimates just by fixing the reach to 150, and they didn't make a lot of sense. The estimates that we were getting were very, very low. So probably this 60 is not too far from a good Dunbar number to apply to this particular problem.
Okay, I think that we reached the end of the seminar. So thank you very much again, Antonio, for this presentation.